Welcome back to QHSE Talks.
Hi.
Picture this for a second.
Sure.
You are sitting in a crane cab.
Okay.
You're manipulating a 10,000-pound steel beam, like 20 stories in the air.
High stakes right there.
Exactly. And a sudden gust of wind hits, causing the load to drift just a little bit. You check your load indicator, and you are right on the edge of the capacity chart.
Oh, man, that's the worst feeling.
Right. And meanwhile, your radio is just crackling. You've got a site manager screaming about a concrete pour that is delayed, and it's costing the project thousands of dollars a minute.
Yeah, the pressure is on.
So what do? Do you push through and make the lift, or, do you shut the entire site down?
It's a heavy choice.
Literally.
It really is. Today, we are immersing ourselves in the just unforgiving physics of hoisting and rigging.
Yeah.
Whether you're an aspiring safety professional prepping for the ASP 11 exam.
Specifically Domain 2, Topic 8, Part F.
Yeah.
Right. Yes, exactly. Or, if you're a site manager currently overseeing complex lifts out in the field, this QHSE Talks is basically your ultimate field manual.
Absolutely.
Our mission today is to thoroughly master the key safety fundamentals that keep, thousands of tons of steel suspended safely in the air.
Because it's not magic. It's physics.
Right. And we are pulling from a serious stack of source material today. We've got the OSHA Construction Safety and Health Standards, specifically subparts H and N.
The heavy hitters?
Yeah. Plus the Bechtel Rigging Handbook, rigorous CSP and ASP exam practice problems, engineering safety manuals, and even the IOSH lifting equation.
Oh, the human element. That's crucial.
We are pulling all of this together to give you the comprehensive understanding required, not just to pass a certification test, but to actually keep people alive on a job site.
Because hoisting and rigging isn't just about massive machinery or learning how to read a load chart. It is this constant, unforgiving battle against gravity. It's where mechanical engineering, human psychology, and strict regulatory compliance all just violently intersect.
Violently intersect. I like that.
Yeah, a single miscalculation on paper or even a brief lapse in judgment in the field, it doesn't just mean you fail an exam.
No.
It brings the entire physical world crashing down. The stakes literally do not get any higher in the construction and safety industry.
Okay, let's unpack this, starting right inside that high-stakes scenario we just pictured in the crane cab.
The screaming site manager scenario.
Yeah, exactly. The most critical concept in our sources regarding operator authority is called stop work authority.
Essential.
And the texts are incredibly explicit here. Whenever there is any doubt regarding safety, the crane operator has the absolute unquestionable authority to stop and refuse to handle loads.
Period.
Right. And that halt remains in effect until a qualified person determines that safety has been assured. Now, if I'm a site manager listening to this, I might feel a bit of tension here, It sounds like the regulatory framework completely shields the operator's right to halt the lift, regardless of the financial pressure.
What's fascinating here is the psychological weight of that specific regulatory design.
How so?
Well, stop work authority intentionally shifts the ultimate safety burden from the site manager.
Who might be miles away.
Exactly. They might be in a trailer, blinded by budget spreadsheets and schedule pressures. It shifts it directly to the person sitting in the cab.
Because they're the ones actually feeling it.
Yeah, the operator's the one feeling the wind shear against the boom. They're monitoring the ground conditions out the window, feeling the subtle physical vibrations of the machine, translating right through the seat.
Wow. Yeah, you can't put a price on that situational awareness.
You really can't. OSHA regulations protect the operator by making it a severe compliance violation to override their safety halt without a formal assessment.
And notice the phrasing the standard uses. It doesn't say the lift resumes until the boss says it's okay.
Right, no.
It specifically requires a qualified person.
And a qualified person, in regulatory terms, means someone with a recognized degree, certificate, or professional standing.
So not just anyone with a clipboard.
No, it has to be someone who has extensively demonstrated their ability to resolve problems relating to this subject matter. It was a highly specific, legally binding designation.
Precisely. The operator must understand signs, signals, and load charts intimately because they are the last fail-safe in a highly complex chain of events.
Right. If the operator says no, the lift does not happen. period.
I'm looking at the Bechtel rigging handbook, and it emphasizes that accidents are so heavily driven by human factors.
So overwhelmingly.
Operators obviously have to be certified by accredited organizations, like the National Commission for the Certification of Crane Operators.
Sure.
And they must be physically and mentally fit. But the onboarding process really stood out to me here.
Yeah, the shadowing.
Right. Upon employment, a new operator doesn't just jump into the cab, wave to the foreman, and start swinging steel.
That would be a disaster.
It says they have to be assigned to work with the crane and rigging foreman, and they must be shadowed on selective jobs for a period of not less than 1 week.
That mandatory monitoring period acknowledges a really vital truth. Every job site has its own unique ecosystem.
Ecosystem, yeah, that's a good word for it.
A piece of paper certifying you know how to operate a crane does not mean you understand the specific communication quirks of this site's signal person.
Oh, that's true. Hand signals can vary slightly, or just people have their own style.
Exactly. Or, you might not know the specific blind spots of this particular congested urban layout. You need time to adjust.
Which brings us to the physical foundation of the site itself. You can have the most experienced operator in the world.
Backed by a brilliant site manager.
Right, but if the ground beneath the crane gives way, none of that matters.
Game over.
Our sources mandate that equipment must be leveled, and the operator is responsible for checking the ground conditions around the hoisting equipment. I want to look closer at what ground conditions actually means mechanically.
It's way more than just checking for a puddle.
Right. They are looking for ground settling under the outriggers, groundwater accumulation, and changes in soil-bearing capacity.
Soil-bearing capacity is it's the invisible variable that causes so many catastrophic tipping incidents.
Really? Just the soil?
Yeah, think about what a crane's outrigger pad is doing. It is taking the immense dynamic weight of a swinging crane and a suspended load and concentrating all of that force down into a few square feet of earth.
That's an unbelievable amount of pressure.
It is. And different soils have wildly different bearing capacities. I mean, the amount of pressure the ground can withstand before it simply shears and gives way.
Like solid bedrock versus sand?
Exactly. Solid bedrock might support 100 tons per square foot. Loose, sandy soil or wet clay might only support 1 or 2 tons. If there has been heavy rain, or if groundwater is accumulating invisibly beneath the surface.
You can't even see from the cab.
Right. That hydrostatic pressure completely changes the friction between the soil particles. The ground essentially turns into a liquid under extreme pressure.
That is terrifying.
So when the standard says the crane must be leveled, it doesn't just mean at the start of the day. It means monitoring those outrigger pads continuously.
Because things shift.
If one pad sinks even a fraction of an inch into wet clay, the entire center of gravity of the crane shifts, throwing the load charts completely out the window.
I want to transition into the math side of that center of gravity because for anyone taking the ASP Exam Domain 1, Topic 2 specifically tests rigging and load calculations.
Oh yeah, get your calculators ready.
Yeah, there is a really illuminating scenario in the practice problems that illustrates exactly how a crane balances these massive forces.
Tower crane problem.
Yes. So imagine a tower crane. It has a main boom that extends 100 feet forward from the cab.
Okay, 100 feet.
Behind the cab, there is a short boom specifically for the counterweight that is 20 feet long. The heavy counterweight can be moved mechanically along this short 20-foot boom.
Right, to adjust the balance.
Now, the crane operator needs to pick up a 10,000-pound object and place it at a spot exactly 40 feet forward from the cab.
Okay, so we have our variables.
The exam question is, to balance this load, where should a 40-ton, which is 80,000 pounds counterweight, be placed on that 20-foot short boom?
This is a classic moment arm calculation.
Let's break that down.
To solve this, you need to balance the torque on both sides of the crane's pivot point, which is the cab.
Torque?
Torque, or a moment of force, is simply the physical weight multiplied by its distance from the pivot point. It measures rotational force.
Like a seesaw.
Exactly. Or imagine pushing a heavy door.
Yeah.
If you push near the hinges, it's incredibly hard to move. If you push at the handle, far away from the hinges, it swings easily. The distance multiplies your force.
Right, so let's look at the forward load side first. We have a 10,000-pound object suspended 40 feet away from the pivot point.
So we multiply those.
We multiply the weight by the distance. 10,000 pounds times 40 feet. That gives us 400,000 foot-pounds of torque pulling down on the main boom, trying to rotate the entire crane forward.
And that 400,000 foot-pounds of rotational force has to be exactly neutralized by the counterweight on the backside.
Okay, so let's look at this short boom. We have a 40-ton counterweight.
The first trick on the exam is unit consistency, though.
Oh, right, because we use pounds for the front.
Exactly. Our forward load was calculated in pounds, so we must convert the counterweight from tons to pounds.
1 ton is 2,000 pounds.
So our 40-ton counterweight is 80,000 pounds.
Okay, so we know the force pushing down on the back is 80,000 pounds, and we know the target torque we need to match to prevent the crane from tipping over is 400,000 foot-pounds.
Right.
So our equation is 80,000 pounds multiplied by some unknown distance equals 400,000 foot-pounds.
Basic algebra from here.
To isolate that unknown distance, we divide the total target torque by the weight of the counterweight. 400,000 divided by 80,000 gives us exactly 5.
Meaning the counterweight must be placed exactly 5 feet along the short boom.
Just 5 feet.
Just 5 feet. And this exposes the terrifying reality of geometric leverage.
It really does.
A massive 80,000-pound hunk of steel only needs to move 5 feet from the center pivot to completely neutralize a 10,000-pound load hanging 40 feet away in the air.
A crane is essentially a giant teetering seesaw.
Held back from disaster only by the strict enforcement of that mathematics.
And that mathematical tension doesn't just exist in the massive steel structure of the crane. It is acutely concentrated in the rigging itself, the hardware and slings physically connecting the hook to the load.
The micro level of the left.
According to the Bowen EHS practice problems, when you are rigging a piece of equipment, a vertical basket hitch allows the greatest amount of weight to be picked up compared to a single leg, a double leg, or a choker hitch.
If we look closely at how a vertical basket hitch is physically constructed, the physics become very clear.
Walk us through it.
In a vertical basket hitch, the sling goes under the load, and both ends of the sling are brought back up and attached directly to the hook.
So they hang perfectly straight down.
They hang perfectly vertical. Because the load is now fully supported by 2 parallel vertical legs of the same sling, the lifting capacity is essentially doubled compared to using just a single vertical leg.
You have 2 pillars of steel rope sharing the burden equally.
Exactly.
In stark contrast to a choker hitch, where the sling wraps around the load and the eye of the sling is passed through itself, choking down on the material.
Like a noose.
Right. Why does that configuration reduce the capacity so severely?
Because of the intense shear stress it creates on the wire rope.
Shear stress.
When you choke a sling, you are pulling the wire rope tightly across itself at a severe angle. The steel wires aren't just handling the vertical tension of the load anymore.
What else are they doing?
They're being crushed laterally against each other at the choke point.
Ouch. That brings up a critical metric mentioned in the OSHA standards that governs wire rope capacity, the D/D ratio.
Very important ratio.
It says capacity is heavily affected by this ratio, but what exactly does that mean?
The D/D ratio is the ratio of the diameter of the object you are bending the wire rope round, represented by a capital D, to the diameter of the wire rope itself, represented by a lowercase d.
Okay, big D, little d.
Let's say you have a thick wire rope, maybe 1 inch in diameter. If you bend that rope around a massive, smooth cylinder, like a massive crane sheave.
The big pulleys at the top.
Right, the individual steel wires on the outside of the curve have to stretch slightly, and the ones on the inside compress slightly.
Makes sense.
But the radius is gentle enough that the steel remains within its elastic limits. It bounces back.
But if you take that same thick wire rope and try to bend it around a very sharp corner or like a tiny shackle pin.
Exactly. The capital D becomes very small.
So what happens to the steel?
The wires on the outside of that tight bend are forced to stretch so far that they exceed their yield strength. They literally begin to pull apart and snap at the microscopic level.
While the wires on the inside are crushed.
Yep. A tight D/D ratio permanently damages the structural integrity of the rope, which is why capacity drops drastically when a wire rope is bent around a tight radius.
That structural damage is also why there are strict visual rules for removal. Our sources mandate that if a wire rope choker shows more than 10 broken wires, it is done.
It has to go.
It must be immediately removed from service, not tomorrow, not after the lift, immediately.
And we see that same concern for crushing wires in the infamous U-bolt rule, which is heavily tested on the ASP exam.
Oh, I've heard of this.
When you are properly making an eye in a wire rope using U-bolt clips, you must use at least 3 clips.
3 clips, okay.
But the orientation is what matters. The U-bolt part of the clip must be placed on the dead end of the rope.
The short tail end that isn't carrying the load.
Yes. The saddle part of the clip, which is much wider and smoother, must rest on the live, load-bearing end of the rope.
The old rigging mnemonic for this is never saddle a dead horse, meaning don't put the saddle on the dead end.
That's the one.
But wait, if I think about the physics there, the U-bolt is a thin, rounded piece of steel. If I tighten the nuts on that U-bolt, it concentrates an immense amount of pressure onto a very narrow band of the rope.
You've hit on the exact mechanism of failure.
Oh.
If you put the U-bolt on the live load-bearing end of the rope, that concentrated pressure will crush the internal strands of the wire rope right where it needs to be strongest.
So by placing the wider, smoother saddle on the live end?
You distribute the clamping force over a larger surface area, protecting the structural integrity of the load-bearing wires.
That is so clever.
The dead end, which doesn't carry tension, can take the localized crushing force of the U-bolt without compromising the lift.
And while we are discussing splices, for fiber ropes under 1 inch in diameter, the standards require the tails to provide at least 6 rip diameters beyond the last full tuck when splicing.
Right, to prevent the splice from slipping under tension.
The hardware connecting all of this together is just as scrutinized. Hooks on lower load blocks or overhaul ball assemblies must be safety type hooks.
No open hooks.
Right. This means they are closed and locked, completely eliminating the throat opening. You can't just have an open J-hook where a sudden slack in the line allows the sling to slip out.
That happens more often than you'd think without safety latches.
And for shackles, the safe working loads must be strictly adhered to using standard manufacturer tables. But here is where the math really trips people up in the field. Sling angles.
Oh boy, the silent killer of rigging.
We established that a vertical basket hitch maximizes capacity because the legs are perfectly straight up and down. But when we rig a long beam, we usually use a double leg sling, attaching one leg to each end of the beam, creating a triangle.
Right.
How does that geometry actually multiply the tension on the hardware?
To visualize this, imagine you are holding a heavy grocery bag.
Okay, I've got my groceries.
If you let your arm hang perfectly straight down, your shoulder is supporting the exact weight of the bag.
No problem.
But now, imagine trying to hold that same heavy bag straight out to your side, horizontally.
Oh, my shoulder hurts just thinking about it.
The bag hasn't gotten any heavier, but the tension on your shoulder muscles is suddenly agonizing. You are fighting horizontal leverage.
So when the sling legs are hanging straight down, all of the force is vertical. A 1,000-pound load puts 500 pounds of tension on each leg.
Right.
But the moment you start spreading those legs apart to reach the ends of a long load, you introduce an angle.
And as that angle between the horizontal plane of the load and the sling decreases,
meaning the sling becomes flatter and closer to the beam,
the tension on each leg increases exponentially. The vertical lifting force still has to equal the weight of the load, but now you have introduced a massive horizontal force pulling inward on the load, trying to stretch the sling horizontally.
So if the sling angle drops to 30 degrees from the horizontal, what happens to the math?
At 30 degrees, the tension in each leg is equal to the entire weight of the load.
Wait, really? The entire weight?
In our 1,000-pound example, at a 30-degree angle, each sling leg is experiencing 1,000 pounds of tension, not 500.
So the tension has literally doubled purely because of the geometry?
Exactly. This is why you cannot simply look at a sling rated for 1,000 pounds and assume it can lift a 1,000-pound load. You have to calculate the sling angle multiplier.
That geometric multiplication of force is exactly why fatigue, abrasive wear, and abuse are so heavily scrutinized by OSHA.
The wear and tear is relentless.
The rigging components are constantly subjected to these hidden multiplied forces. The standard dictates that slings must be visually inspected by a competent person daily prior to use.
Daily is key.
For nylon synthetic slings, there are strict visual cues. Synthetic slings have colored fibers woven inside the inner core of the jacket.
The telltales.
If you can see that colored fiber core showing through the outer jacket, it physically proves the outer protective layer has worn away against the abrasive edges of the loads.
And the sling is no longer safe for use.
And an equally important administrative control regarding those defective slings, unused or damaged rigging must be immediately removed from the work area.
This isn't just about housekeeping, preventing tripping hazards.
Right, because if a defective sling is left lying near a lift zone, human nature takes over. A worker in a rush, trying to keep up with the schedule, will just grab the nearest piece of equipment.
They see a sling, they use a sling.
By mandating that unused gear is immediately removed and properly stored, you control the physical inventory. You ensure that only inspected appropriate gear can be introduced into the lift operation.
If we connect this intense scrutiny of rigging to the bigger picture, lifting a load of steel structural beams is one thing.
It's expensive, but it's steel.
Right. If a rigging component fails and a beam drops, it is a massive financial loss, a major schedule delay, and a terrifying near-miss investigation.
Absolutely.
But when we transition into lifting human beings, the regulatory framework changes entirely because all tolerance for mechanical failure is removed.
Here's where it gets really interesting. When lifting personnel on a platform, the combined weight of the load, the platform itself, and the rigging must not exceed 50% of the crane's rated capacity for that specific radius and configuration.
They cut it in half.
OSHA forces you to cut the capacity chart right in half immediately.
That 50% rule is a massive engineering safety factor.
It seems like a lot, right?
It ensures that the crane is operating so incredibly far below its tipping point or structural failure point that sudden environmental variables, like a microburst of wind hitting the surface area of the platform, cannot push the machine over the edge.
Or like dynamic shock loading from the crane stopping abruptly.
Exactly. Furthermore, when a wire rope bridle is used to connect the personnel platform to the load line, each bridle leg must connect to a master link or shackle.
So you cannot just hook them all onto the crane hook individually.
No, absolutely not. The master link ensures the load is perfectly evenly divided among all the legs, preventing one leg from taking the brunt of the force and snapping.
But despite cutting the capacity in half, and despite having a competent person verify the master link and rigging, OSHA still mandates a trial lift.
A mandatory dry run.
A trial lift must be performed with the platform unoccupied, but loaded to the anticipated lift weight with sandbags or steel. It must travel to each new work location, checking for twisted lines or slack.
Right.
And immediately following that trial run, a competent person has to conduct another thorough visual inspection of the crane, the rigging, the platform, and the ground support.
Redundancy upon redundancy.
So if we trust our math and we trust the 50% capacity rule, why do we mandate testing the platform unoccupied first? What are we looking for?
Because mathematics and load charts exist in a perfect theoretical vacuum.
Right, on paper.
The real world of a construction site does not. The unoccupied trial lift is designed to catch the invisible, dynamic variables that static calculations simply cannot predict.
Like what?
For instance, when a load is actually suspended and the crane begins to swing, how does the specific hydrostatic pressure of the soil beneath the outriggers respond to that shifting center of gravity?
Oh, going back to the soil-bearing capacity.
Exactly. Or does a hydraulic valve on the boom have a microscopic leak that only reveals itself when the boom is moving under active pressurized load?
Wow, yeah.
Are the multiple part lines of the hoist rope twisting around each other as the block lowers, which could cause the platform to spin violently?
Oh, that makes sense. The trial lift forces the mechanical equipment to prove its integrity in the exact physical space where the human beings are about to travel.
It's the ultimate reality check.
It tests the seating of the brakes, the even spooling of the wire rope on the drum, and the physical clearances around nearby structures.
And before any of that mechanical testing even occurs, there are mandatory pre-lift meetings.
Getting everyone on the same page.
These are required for all personnel involved. The crane operator, the signal person, the employees who are going to be hoisted, and the person responsible for the task.
When do they happen?
This meeting happens prior to the trial lift at each new location and must be repeated from scratch if any new employees are assigned to the operation.
That makes sense.
The entire operation hinges on absolute communication clarity because a misunderstanding between the signal person and the operator when humans are suspended in the air is lethal.
That communication challenge is amplified exponentially in the other high-stakes operation our sources detail.
Right.
Rotorcraft or, helicopter lifts.
Oh, man. A totally different beast.
This is a highly specialized lifting method with incredibly unique physical hazards. The downwash from the helicopter rotors is essentially a localized, sustained hurricane.
It is. The aerodynamic physics of a helicopter require it to push a massive column of air straight down to maintain lift.
And it has to go somewhere.
When that column of air hits the ground, it spreads out laterally at high speeds. This creates severe hazards that just don't exist under a tower crane.
The OSHA standards are very specific about mitigating this. Workers receiving loads under helicopter must wear complete eye protection and hard hats with secured chin straps.
Because the downwash will rip a standard hard hat right off their head.
Exactly. Loose-fitting clothing is totally banned. You can't wear an unzipped jacket because it will flap violently in the downwash and become a severe snag hazard on the moving hoist line.
That's terrifying to picture.
Furthermore, all loose gear within 100 feet of the lifting area, the depositing area, and any other area susceptible to the rotor downwash must be completely cleared or heavily secured.
That 100-foot clearance zone is critical because rotor downwash can turn a forgotten piece of plywood, an empty bucket, or a loose hand tool into a lethal high-velocity projectile.
Like flying shrapnel.
Yes. Working under a helicopter requires a completely different risk assessment model. You are dealing with intense noise, which makes verbal communication nearly impossible.
So hand signals are everything.
Everything. Plus, extreme aerodynamic forces, static electricity buildup from the rotors moving through the air.
Wait, static electricity?
Oh yeah, massive amounts of it. And the terrifying reality that an aircraft cannot simply stop and lock its brakes in midair with the same rigid stability as a crane tied to the earth.
That extreme lack of rigid stability under a helicopter perfectly illustrates why controlling the center of gravity is so vital.
Absolutely.
And nowhere is the center of gravity more difficult to control than when you are lifting multiple separate pieces of steel on a single line at the same time. This brings us to the art of critical lifts and multiple lift rigging, often called Christmas treeing in the steel erection industry.
A very apt name. To manage the risk of these operations, the Bechtel Rigging Handbook gives us a very clear taxonomy of rigging levels to determine the necessary administrative controls.
Break those down for us.
They define light rigging as lifting items up to 10 tons. Medium rigging is between 10 and 50 tons. But then we have critical rigging.
And critical rigging isn't just about weight, right?
Not at all.
It's defined as any crane lift that exceeds 90% of the crane's rated capacity chart. Any lift requiring 2 cranes to operate simultaneously on a single load.
Which is a logistical nightmare.
Or any lift occurring over power lines, operating facilities, or active process pipe racks.
Correct. Defining those tiers is an excellent management control because it triggers mandatory levels of administrative oversight.
The paperwork catches up with the physics.
Exactly. A critical lift requires a formal, written lift plan, extensive engineering calculations detailing the exact center of gravity, and sign-offs from multiple levels of site management before the crane is even turned on.
So let's look at the multiple lift rigging procedure, or Christmas treeing, which falls under this intense scrutiny.
Okay.
This is where a single crane lifts a whole series of structural steel beams at the same time.
Multiple pieces on one line.
The criteria outlined in the OSHA standards are incredibly strict here. You are allowed a maximum of 5 members hoisted per lift. Only structural beams or similar members are allowed.
No random materials.
The members must be rigged at least 7 feet apart on the line, and the assembly must be rigged from the top down, but the members must be set from the bottom up.
That's the sequence.
Let me think about the physical logistics of that sequence. If I'm rigging from the top down, that means the first beam I attach to the main hoist line is going to be the highest one in the air.
Right.
Then I attach the next beam 7 feet below it, and so on, until I have 5 beams hanging in a vertical line.
Exactly. Now visualize the crane swinging that massive dangling assembly over to the steel structure of the building where the connectors, the iron workers, are waiting to bolt them into place.
Wait, if I try to set that top beam first? Oh, I see the danger.
What?
If I maneuver the top beam into place, the other 4 heavy steel beams are dangling directly below the connection point, swinging wildly right into the chest and legs of the ironworkers standing on the lower floor.
You've just hit on the exact catastrophic scenario this sequence is designed to prevent.
That is scary.
Setting from the bottom up ensures that when the connectors grab the lowest beam on the line, the rest of the load is securely suspended high above their heads, totally clear of their immediate physical work zone.
So they are working underneath safety, basically.
Once they bolt that bottom beam in, the crane lowers the hoist line 7 feet, and the next beam comes down into their workspace.
That is a brilliant logistical control. And because this multiple lift operation introduces so much dynamic motion and swinging, the safety factors are mathematically amplified.
They have to be.
The standard mandates that components of the multiple lift rigging assembly must be specifically designed with a 5-to-1 safety factor.
Which means if a multiple lift rigging component is rated to carry a 1,000-pound load, it must actually be structurally engineered and manufactured, capable of holding 5,000 pounds before failure.
I find it fascinating to contrast that with other standards in the sources. For example, passenger hoist ropes, elevators lifting humans, require a safety factor of 3.5 times the full rated load.
Right.
Why does lifting steel beams require a 5-to-1 factor when lifting humans only requires 3.5 to 1?
It comes down to the physics of dynamic shock loading.
Okay, unpack that.
A passenger hoist travels on fixed guide rails in an enclosed shaft. The motion is smooth, controlled, and perfectly vertical.
It can't swing.
Exactly. A multiple lift assembly, however, involves 5 separate steel beams suspended in open air. If a sudden gust of wind hits, or if the crane operator brakes too aggressively, those beams can swing, bounce, and transfer massive kinetic shock loads into the rigging hardware.
So the hardware has to absorb all that bounce.
The regulators mathematically weight the risk of that dynamic, unguided shock loading higher than the smooth, guided lift of an elevator.
Managing those complex physics requires clearly defined roles on the site. The sources differentiate heavily between the rigging engineer and the rigging supervisor or specialist.
Do very different jobs.
The rigging engineer is the technical mind. They perform the mathematical calculations, draw up the lift plans, verify the centers of gravity, and ensure the 5-to-1 safety factors are geometrically met.
The theorist.
Right. The rigging supervisor, however, is the field general. They are responsible for taking the engineer's theoretical plan and executing it in the messy reality of the job site. They direct the crew and actively manage the physical environment. You cannot have one without the other.
But unfortunately, the gap between the theoretical engineering plan and the physical execution in the field is exactly where catastrophic failures occur.
Yeah.
When an OSHA inspector walks onto a site with heavy hoisting operations, they aren't just looking around randomly. They know the exact physical failure points to target.
The Handbook of OSHA Construction Safety and Health lists the top citations related to rigging.
The usual suspects.
These include administrative failures like having no inspection of riggings for defects prior to use, or the lack of an informed, competent person on site.
Easy citations to write.
But they also look for physical indicators like missing tags on synthetic or chain slings. Because if there's no manufacturer tag, you literally cannot verify the capacity or the material, making it entirely unsafe to use.
If it doesn't have a tag, it's trash.
They also cite for the use of defective alloy chains.
Yeah.
But there is one citation that stands out to me crucially. OSHA heavily penalizes companies manufacturing their own lifting devices.
Oh yeah, they hate that.
If you're a site manager listening to this, you've probably felt the temptation to let a crew weld a quick custom lifting lug onto a beam just to keep a job moving. Construction is full of highly skilled fabricators and welders who work with steel all day. Why is OSHA so specifically aggressive against them making a quick custom lifting bracket?
Because a highly skilled welder might look at a massive steel motor casing and think, I'll just weld a heavy D-ring onto this casing to give the crane hook a pick point. Steel is steel.
Sounds logical in the moment.
But that fabricator, no matter how skilled with a torch, is not a metallurgical engineer. They have not mathematically calculated the sheer strength of that specific weld under a dynamic, swinging load.
They're just eyeballing it.
More importantly, they haven't accounted for the heat-affected zone, or HAZ.
What happens in the heat-affected zone?
When you apply the extreme heat of a welding torch to steel, you physically alter the crystalline structure of the metal surrounding the weld. You might make it brittle, so the weld itself might hold, but the altered, brittle steel right next to the weld might tear away like perforated paper under tension.
That's a terrifying mental image.
Manufactured proprietary lifting devices undergo rigorous destructive testing, proof loading, and metallurgical analysis to guarantee that 5-to-1 safety factor we discussed earlier.
A custom welded bracket on a job site has zero engineering validation.
OSHA aggressively penalizes this because it is a complete circumvention of the engineering controls designed to prevent loads from dropping out of the sky.
The inspector is also going to look closely at spatial clearances, particularly electrical lines. Loads, booms, and rigging must never approach within 10 feet of energized electrical lines rated 50 kV or lower.
10 feet is the minimum.
kV stands for kilovolts, so that's 50,000 volts. If the lines are over 50 kV, the clearance distance increases further. Why is the 10-foot rule so strict? It's not just about bumping to the wire, is it?
No, it's about the physics of high voltage.
Yeah.
Electricity at that immense pressure wants to find the fastest path to the ground. It doesn't need the crane boom to physically touch the wire. High voltage can jump, or arc, through the air, ionizing the air molecules to create a conductive path.
Like lightning.
Exactly like lightning. Because a crane is a massive, towering steel structure tied directly to the earth, it acts as a giant lightning rod.
So if you get too close.
If the boom swings within the arcing distance of that 50 kV line, the electricity will leak through the air, travel down the boom through the cab and into the ground, instantly electrocuting anyone touching the machine or the suspended load.
We also see strict mechanical rules regarding the crane's drum itself. The standards state there must always be at least 2 full wraps of wire rope cable on the hoist drum at all times of operation.
You can never spool the cable all the way out until you see the bare drum.
Right. Why 2 wraps?
That 2-wrap rule is a brilliant mechanical safeguard, utilizing friction. When wire rope is wrapped tightly around the steel drum, the friction of those wraps absorbs the immense tension of the suspended load.
Oh, I see.
The anchor point, the physical mechanical pin where the end of the wire rope attaches to the inside of the drum, is not designed to hold 10,000 pounds.
It's just a pin.
If you unwind the cable all the way down to that anchor, the friction is gone, and the entire weight of the load pulls directly on that single small mechanical pin, which will shear right off. The 2 wraps of cable maintain the friction necessary to protect the anchor.
To control that swinging load once it's in the air, the sources dictate the strict use of taglines. Taglines are ropes attached to the load that workers on the ground hold onto.
Ground control.
Their sole purpose is to control the rotation of the load, prevent swinging, and most importantly, keep workers physically away from the danger zone. You shouldn't have workers trying to muscle a suspended steel beam into place with their bare hands while standing directly underneath the shadow of the load.
Which perfectly transitions us into the final technical aspect of our analysis. Because while we spend an immense amount of time talking about 80,000-pound counterweights, heat-affected zones, and tower cranes, the most common piece of material handling equipment on any job site, and the one most prone to failure, is the human body.
Exactly. Back injuries and musculoskeletal disorders are some of the most common, debilitating, and costly workplace incidents globally.
Without a doubt.
To quantify the physical risk of manual material handling, the National Institute for Occupational Safety and Health developed the NAOH lifting equation. For safety professionals taking the ASP exam, calculating manual lift parameters using this equation is a major component of Domain 1. So let's break down the mechanics of the human machine.
The NAOH lifting equation looks incredibly intimidating on paper, but it is essentially a mathematical model of human biomechanics.
How does it work?
It calculates a recommended weight limit, or RWL, by starting with a standard load constant and multiplying it by 6 different fractional multipliers. These components evaluate every specific movement of the lift.
So it's breaking the lift down into parts.
Yes, you have the vertical component, the vertical multiplier, the distance component, the asymmetry component, which measures twisting.
Twisting your back is always bad.
The frequency multiplier, which measures how often you lift, and the coupling multiplier, which measures how good your grip is on the object.
Let's focus on the geometric variables. The ASP exam heavily tests. The sources give a brilliant exam strategy called Spot the Zero.
Love this trick.
The Board of Certified Safety Professionals loves to include trick questions to see if you actually understand the physical, biomechanical limits of the equation before you start blindly punching numbers into a calculator.
They want to see if you intuitively get it.
The trick is this. The horizontal distance, h, is the distance of the load from the midpoint between your inner ankle bones. If that horizontal distance reaches 26 inches away from your body, the mathematical horizontal multiplier drops to exactly 0.
This raises a fundamental mathematical reality. What happens when you multiply a long string of complex numbers by 0?
The entire product becomes 0.
So if the horizontal multiplier is 0, the recommended weight limit becomes 0. You can answer the exam question in 5 seconds without touching your calculator.
That is a great tip for the exam.
But the biomechanical reality behind that math is what actually matters in the field. Reaching your arms out 26 inches horizontally to lift a load puts such massive moment arm torque on the L5-S1 spinal disc.
The hinge point at the very base of your lumbar spine.
That the equation deems absolutely no weight to be safe to lift.
The exam tips also tell us to memorize the physical constants of the human machine. You need to know that the absolute maximum load constant under perfect ideal conditions is 51 pounds.
That's the baseline.
The ideal horizontal distance, h, is 10 inches, which basically means holding the box right against your stomach.
Close to the center of gravity.
And the ideal vertical distance, v, is 30 inches, which is roughly knuckle height when your arms are hanging relaxed at your sides, meaning you don't have to stoop down to the floor or reach up over your head to grasp the load.
And when a worker's job task results in a high lifting index, meaning the actual physical weight of the load exceeds the recommended weight limit calculated by the equation, we have to look at the hierarchy of controls to fix the problem.
What's the best fix?
From a purely ergonomic and mathematical standpoint, what yields the highest mathematical improvement to the equation? It is always bringing the load closer to the body. Reducing that horizontal distance h has the most dramatic exponential impact on reducing torque on the L5-S1 disc.
So what does this all mean? If I'm looking at this structurally, is the human body essentially just a biological crane?
That's one way to look at it.
Our lumbar spine acts as the boom, our body weight behind our hips acts as the counterweight, and our outstretched arms are the rigging.
That is a phenomenal, highly accurate analogy, yes. When a tower crane extends its boom horizontally, its lifting capacity drops massively due to the moment arm torque we calculated earlier.
Right.
When you extend your arms horizontally to pick up a box, the capacity of your lower back drops for the exact same physical reason. The immutable principles of physical leverage, center of gravity stability, and structural tension apply exactly the same, whether you are lifting a 10-ton structural steel beam with a diesel engine or a 50-pound bag of cement with your own skeletal structure.
That brings us full circle perfectly. As we wrap up this session, let's reflect on the immense physical reality we've explored today.
We covered a lot of ground.
We really did. We started inside the crane cab, unpacking the intense psychological and legal responsibility of the operator's stop work authority.
The ultimate failsafe.
We walked through the microscopic destruction of wire ropes bending over tight DD ratios and memorized the crushing physics behind the U-bolt rule.
Never saddle a dead horse.
Exactly. We explored the intense geometry of sling angles, visualizing how flattening out a sling horizontally geometrically multiplies the tension tearing at the hardware.
A grocery bag analogy.
We discussed the zero-tolerance engineering required for lifting humans, utilizing a 50% capacity cut in unoccupied trial lifts to catch invisible dynamic variables, and we navigated the chaotic, hurricane-force downwash hazards of helicopters.
Rotorcraft are no joke.
We walked through the top-down rigging and bottom-up setting of multiple steel lifts to keep dangling beams away from ironworkers, and explored the metallurgical, heat-affected zones that cause OSHA to heavily cite custom-welded lifting lugs.
Keep the welders away from the lifting gear.
And finally, we scaled all of those massive physics down to the microscopic level of the human spine using the NIOS lifting equation. Mastering this material isn't just about passing Domain 2 of the ASP exam, it's about understanding the physical laws governing the world around you.
Absolutely.
You are the safety professional who ensures the math is right, the gear is physically sound, and the people get to go home to their families.
And I want to leave you with a final concept to mull over as we look to the future of our profession.
Okay, what is it?
We spend an immense amount of time heavily regulating the mechanical breakdown of wire ropes, the exact placement of U-bolts, and the precise geometry of sling angles.
Right, all physical things.
But as artificial intelligence and cloud computing begin to calculate our dynamic lift plans in real time, and as cranes become increasingly capable of remote or even fully autonomous operation, a fundamental shift is rapidly approaching.
Oh, wow.
Will the ultimate stop work authority shift from the human operator sitting in the cab, feeling the wind against the glass and the vibration in the seat, to a predictive AI algorithm operating in a server farm miles away?
It's wild to think about.
And if that happens, if we trust the machine to mathematically monitor its own stability parameters, what new invisible blind spots might that create for the safety professionals of tomorrow?
That is a staggering thought to consider. The laws of physics won't change, but who or what enforces them might. Thank you for joining us on this extensive QHSE Talks into hoisting and rigging. Until next time, keep studying, stay curious, and stay safe out there.